Today we're going to talk about regression wisdom. One of the things that you need to be concerned about is extrapolation. Let's look at the following scatter plot. On the x-axis we have year, and on the y-axis we have the men's age when they first get married. You can see that as the years have progressed, the age in which men first marry has decreased. We have fitted a line of best fit. We got y hat equals negative 0.0531x plus 126.67. Linear models do a good job of predicting y values within the data. However, outside the range of x values, prediction is called extrapolation. If we were to extrapolate to the year 2050, it turns out, based on our line of best fit, that the average men's age in which they first marry is 17.8 years old. Now, that really doesn't make much sense, because if we were to go in further, you could see that the age would decrease. So when you're predicting, you should always use values within the x values that are given. Outlying points can strongly influence the regression. Even a single point far from the body of the data can dominate the analysis. Any point that stands away from the others can be called an outlier and deserve your special attention. The following scatter plot shows that something was awry in Palm Beach County, Florida during the 2000 presidential election. On the x-axis we have the number of voters for Nader, and in the y-axis we have the number of voters for Buchanan. You can see that the body of the scatter plot is down here, and we have this one point that's up here marked with the X. The red line shows the effects that one unusual point can have on the regression. If we include this point, you see that the red line has a steeper slope than the blue line. The blue line does not include this point. So the slope of the line has changed dramatically because of this one point. This point would be called an influential point. The linear model doesn't fit points with large residuals very well. Because they seem to be different from other cases, it is important to pay special attention to points with large residuals. So if we take the following, we have shoe size versus IQ. We see the body of the scatter points down here, and we have this one point that's the X. If accidentally we mistype that value, and it actually turns out to be down here, which is on the right graph, you can see that the slope of the line has changed dramatically, from a positive to a negative. This point is called an influential point. You cannot simply delete unusual points from the data. You can, however, fit a model with and without these points as long as you examine and discuss the two regression models to understand how they differ. No matter how strong the association, no matter how large the R-squared value, no matter how straight the line, there is no way to conclude from a regression alone that one variable causes the other. There's always the possibility that some third variable is driving both of the variables you have observed. With observational data, as opposed to data from a designed experiment, there is no way to be sure that a lurking variable is not the cause of any apparent association. The following scatter plot shows the average life expectancy for a country is related to the number of doctors per person in that country. This scatter plot shows the average life expectancy for a country is related to the number of televisions per person in that country. Since televisions are cheaper than doctors, sending TVs to countries with low life expectancies in order to extend lifetimes, right? How about considering a lurking variable? That makes more sense. Countries with higher standards of living have both longer life expectancies and more doctors and TVs. If higher living standards cause changes in these other variables, improving life standards might be expected to prolong lives and increase the number of doctors and TVs.